welcome you once again, sir. Now, I would like to invite Dr. Subramanyam, sir, take up the session.
Hello.
Yes, sir. Yes, sir. Kindly proceed, sir.
I try to share my presentation. Hello. Could you please see the
Yes, sir. Yes, sir.
screen?
Your PPT is shared, sir.
Okay, okay. Good afternoon, friends. Thank you for
Sir,
my
maximize the view, sir. Slide. View.
already maximized. I don't know. I could see the. Let me close it.
Sir, please send assignment link, please.
Okay. It is visible now.
Yes, sir. Kindly proceed, sir.
Okay. And thank you for a nice introduction. So, my name is Subramanyam from Hyderabad. So, my company name is Siri Exergy. So, this Exergy name because when we are doing a project work somewhere in 88, 89, at that time one of my roommate took as a project because then I want to start my own company in 2008, almost after 20 years. I thought what are the, because everybody having energy company name, so I thought okay, we should have a different. So that's why I kept my company name as Siri Exergy. But Exergy wise, people are talking about okay, analysis of Exergy and all. But practically once from our company side, because though we have done so many audits, so many I think because we have mentioned so many power plant audits and also some other industry audits, but Exergy analysis we are not doing much practically speaking, other than guiding some people and their want to do some internship or project work. So we'll see some of my works and all where we can able to apply Exergy in power plant, particularly because we are talking about Exergy analysis in thermal power plant and thermodynamics. So we know what is the power plant efficiency. Many people may not be, because whatever we are giving 100% input as a thermal energy, finally what we are getting hardly 33-34% is the final efficiency of overall power plant. 33-34, that too it is a very good plant, very good. Even in the super thermal say 500 megawatt. Nowadays we are going for supercritical and ultra supercritical boilers, but practically what we are getting only 32-33% efficiency. So remaining almost 65% energy we are losing. So 65% energy we are losing based on the first law of analysis, whatever you do energy analysis. So we'll try to analyze. So where are the major possibilities we can able to improve the efficiency of the power plant, either at the design stage, okay. But most of the time our audits we'll do in the because we are doing audit after the installation. Plant is working, so plant is already working for the past 5-10 years, and we'll try to improve their efficiency at least to the design level. But because many times even very difficult even to achieve the design efficiencies. So we'll see what are the areas we can able to concentrate to improve a performance, either in the term of energy efficiency or in terms of Exergy efficiency. Maybe we'll take up 2 examples. One about Exergy analysis of one condenser, another one is on CW pump. So those things we will cover in my presentation. So just I am giving one example. Even if you, because we have so many power plants, almost 300 odd power plants are there in India. Even if you improve even 1%, so 1% efficiency, because we talked about efficiency is hardly 33-34%. 33 to 34% is efficiency. So that means large gap is there to further improve. So even if you improve 1% of our at national level, it is equivalent almost to 12,100 crores per year. So 1%. So that means even at the but though we are generating at 33%, finally again when you physically when finally it is reaching the consumer, that is when your house or your factory and your college you are receiving. So there is again a further loss of transmission distribution losses. So imagine if you are able to improve either in transmission distribution 1% or in the generation side 1%, there is a huge benefit. So huge benefit, and also we can able to even save not only in rupee terms and also the CO2 emissions, because we are now talking about climate change, greenhouse gas emissions, and the temperature rise globally, global warming, these things, etc. So we'll see how we can able to improve, and we have seen the different levels of performance, because I was telling about we have power plants. There is some power plants even as old as in 40-50 years old power plants also working in India. And recently only we are talking about supercritical. So so over a period there are a lot of improvement. So I am giving because though we are talking about Exergy, but in physics still we are more familiar with the heat rate. So heat rate in a sense, suppose you want to produce 1 unit of power. 1 unit of power, what is the heat energy required? So that is varying. Earlier in 60s, it should be somewhere around 2,500. Now the latest plants, innovative plants, we can able to reduce it to 2294. That means hardly there is improvement of 300 kilocalories over a period. So that too over a period of 50-60 years. 50-60 years we can able to improve by the design stages. There are design changes in the system. So now we can able to further, because it is a overall. So overall heat rate could be the say 2500, though I take it is 1960s 60s or 70s design data, still our power plants are even consuming more than 3500. Imagine out of 300 power plants, still many power plants are consuming more than 3000 kilocalories, and you can imagine what is the efficiency. So efficiency of the power plants as low even 20%. 20% also we are operating, and it is misusing, that is wasting our energy, and also if you calculate what is now, I'll give you one more example. So where we are using, so where we are using, this is the power plant. So power plant consume almost 50% of our energy. So power plants alone, if you take the energy intensive industries in India, like it is the power, steel, cement, fertilizer, sponge iron, or textile, aluminum, paper, chloralkali. We take almost 50% of energy goes only is consumed in the power plant. So that means there is a huge potential. That's why these industries are called as now designated consumers under Bureau of Energy Efficiency. So now, based on the potential available, suppose you want to reduce our emissions, or because in the Paris Agreement we are committed that by 2030 to 2030 we should able to reduce our emissions by 33%. 33%, that is the target. So we want to reduce 33%. So major contributor the power plants. So there is a based on the estimates we can able to reduce almost 48%. So just by concentrating on power plants we can able to reduce our emissions 48%. That is called under PAT, that is perform, achieve and trade. So so I will talk about PAT later. So now, so based on our experience, because we will try to evaluate efficiency, because we told about there is a overall efficiency of 33% or 34% is the generation efficiency. Again, because whatever you are generating, it is not exported. Whatever you suppose it is a 500 megawatt plant, 500 megawatt, almost all 6 to 7% is internally consumed. So you have to operate the plant. So what to operate the plant? There is a boiler has to run. There is a mills. There is ID fan, FD fan, boiler feed water pump, CW pumps. There are offsets, coal handling plant. There is the AC plant. There is a cooling tower system operated, air compressors, and AC plant. Lighting. So these are so many equipment has to be operated. For that again we will be consuming somewhere around 10%. So finally you can able to take the overall efficiency. Once whatever put into say 100 units of power or energy, 100 units of energy, finally what is going out is only hardly around 25%. So remaining is again internally consumed. Finally it is one is into the generation and also in the operating your auxiliary equipment. So we have done a number of audits, right from 110 megawatt, these old plants, and 210 megawatt, 500 plants. So again, we have further classified where are the scope areas for further improvement. This is called auxiliary power consumption. So like BFPs, that is boiler feed water pumps. So almost they consume 25%. 25% they consume. CEPs, that is condensate extraction pumps after condenser, again another 3 to 4%. CDW pumps, they consume almost another 10%. ID fans, FD fans, PA fans, mills, CT fans. So that means we do as a part of energy audit. We suppose we know that is around 5% is 5 to 6% is energy consumption of auxiliary. So we further evaluate where is the scope areas or where is the major consumer in the power plant. Like similarly in your college. So college may suppose you are getting a bill of say 10 lakh rupees. So majority power consumption is towards lighting and also ACs, air conditioning. So in fact we have hardly some few pumps and some maybe up to some fans may be consuming. So like that we will do the energy audit. So energy audit maybe because whatever doing energy audit further we can able to further do the Exergy analysis later. So we'll come later. We'll do how we can able to do the Exergy analysis for all this equipment. All this equipment we can able to do it and see where the scope for further improvement. So same thing, whatever I showed earlier, it is in the percentage. So you can see APC means auxiliary power consumption for a typical 210 megawatt. So 210 megawatt, majority of the BFPs nowadays, of course, in supercritical boilers or super thermal boilers, there is a boiler feed water pump is operated by the steam turbine. So that's why their auxiliary consumption reduces. But of course, they again you will be reducing overall efficiency of this cycle because we are taking some part. So auxiliary steam we are taking from the turbine, we are running one more turbine and operating it. So there is a different design philosophies to improve the overall efficiency of the system. Now, as I told further, so there is a key result areas because when you say there is a suppose you are operating say 2500 kilocalories is your heat rate. So that is the what value they normally give when we want to so we get an energy audit. So suppose I submit a proposal, they say now I am operating this level, so I have some target because now there is a PAT at a perform achievement trade. There is a target. I have to reduce my target, otherwise they have to pay penalty. So that's why they are coming to us. So all the power plants now they have to mandatorily carry out energy audit, and they come to us so kindly do our energy audit and give our report and give recommendation. So recommendation. So where should I concentrate? Of course, the Exergy analysis and all okay, but is most of the time people are interested in the where we can able to practically implement and show savings so that they can able to avoid not only penalty, they can able to get additional benefit like a incentive. They should able to get some incentive. So that is our prior motive. So what we will do is we will do the efficiency test of boilers because further divide thermal areas. So thermal areas in a power plant, what are the thermal areas? One is major is the boiler. So boiler again we will able to evaluate the efficiency. Either direct method or indirect method, mostly indirect method. Again, efficiency may be as per design, whether it is a BHL design or whatever design. So their efficiencies will be almost 87 to 88%. So balance is the loss. Next is turbine. So we'll be doing a turbine efficiency, either it is a HP turbine, LP turbine, or the intermediate IP turbine, and also next is the condenser. So condenser again we are whatever LP steam is condensed, so that we can be we can able to at least recover the condensate back to the boiler and improve the overall performance of the turbine system. So next is feeders. That is regenerative feeder, that is LP heaters, HP heaters, and in between there is a derater. So those things also we evaluate part of our audit. Then economizers. So already economizers there is from the flue gas from the exit of the boiler. So after your superheaters. So still the temperature of flue gas will be somewhere around 500 degrees centigrade. So that 500 degrees centigrade further we will try to reduce through economizer. Then there is a air preheaters. So further after air preheater there is no further heat recovery. Finally it goes to ESP energy, that is electrostatic precipitator, and to chimney. So these are the thermal areas. So in addition to that, there is, as I said, there is so many equipment has to be operated to run the plant. So the like raw water. So raw water may be some source, maybe some river or canal. So there normally plant, sometimes your raw water system, pumping system will be away from the plant. Sometimes it is a 10 kilometers, 15 kilometers away from the plant. So from there we have to pump it, and they have to treat it. First we have to treat it, then we have to make clarified water, then filter water, fire water, then there is a DM water and drinking water. So that so many operations has to be carried out. Next is the coal handling plant. So because we are coal either from the mines, you will be getting it, then we have to crush it, then we have to size it, then we have to send it to the coal mills. So that is a coal handling plant. So that is again they have to operate it. That is a huge area. So for that is some energy is required. In ash handling plant, again once you coal is burned, the ash is generated. It is a fly ash, it is a bottom ash. So those have to be separated out and has to be, maybe sometimes we have to make it a slurry and send it out to the ash dike, far away place. And also fly ash nowadays people are selling to the cement plants. So for that we have to make arrangement for transport, the dry ash transport through a compressed air system. Then as a compressed air for operate as a process air, also as an instrument air, and also some of the as I said for the ash handling. So refrigeration and air conditioning. So refrigeration and air conditioning is a huge requirement. So some of the plants may have almost more than 1,200 TR, that is tons of refrigeration load will be there, because we have so many cooling, we have control rooms. So we have control rooms, then also ESP, there is a control room, then again so many nowadays VFDs, there is variable speed drives operating. For that again we require air conditioning, and also maybe window AC or split ACs for the service building. So that is another major load. Then lighting. So lighting also huge requirement. Some of the plants having as load high as 4 to 5 megawatt. Like I'm giving example of like a Ramagundam NTPC. So their lighting load is 4 megawatt. Imagine. So that means it is a huge. So areas are there. So all areas will try to address. So we do the analysis, that is particular. Of course we are doing mostly energy analysis and performance equipment, performance analysis of each and every equipment to evaluate their efficiencies and find out where the margins are available when compared to design, and give us our recommendations with cost benefit analysis. So suppose there is a efficiency improvement of boiler, there is a margin 2 to 3%. So there may be problem with the mill, there may be problem with the firing, there may be sometimes there will be problem with the burners. So even from the insulation side, there may be a lot of heat losses in the radiation losses. So those things all will try, and also maybe the major plot will be the major loss we encounter is the excess air. So if there is a excess air, if you're able to control, if you're able to monitor, that is a major benefit. In addition to that, the exit flue gas temperature. Most of the power plants are designed for around 142 exit flue gas temperature, but many times the exit flue gas temperature go as high as 165 degrees centigrade. So that means there is for every 21 degrees there is 1% loss. So those things we will quantify and tell, and we can able to fine tune the boiler to improve the efficiency. So then in addition to that, not only this, there is some more equipment are there in the plant. So we will do further analysis, key result areas. We call it as key result areas, where you can able to do some analysis, and you can able to tell my client, whoever be my client. So for them, so what actually they have to do to improve their performance. Like FD fan, that is supplies our combustion air, ID fans. Then to exhaust whatever flue gas is generated, we have to throw it to the burner. Then boiler feed water pumps, as I told, boiler feed water pumps is the major load. So their consumption is somewhere around more than 30% of the auxiliary consumed is only BFPs. So there is a huge, even if you improve 1 or 2% of BFP performance, so you can able to, because each boiler motor, that is a motor, it will be somewhere around 3.5 megawatt. In the 210 megawatt, in case of it is at 500 megawatt, is the 10 megawatt. One pump itself at 10 megawatt. Imagine we can able to do some minor adjustment. We can able to improve the performance. If we have shown the saving as high as even 500 kW per pump. So 500 kW per pump is, that means 500, imagine with 500 kW, even the entire your one college can be lighted up. So similarly, there is condensate extension pumps. Each boiler will have a minimum two. So one will be standby, two will be working. Imagine some of the power plants will not have only one single boiler. So they will have a five boilers or six boilers. Sometimes nowadays one of the power plant is having even 14 boilers. That means imagine there is a 14 units. They call 14, and total capacity is coming to almost 4,300 megawatt single power plant. So imagine that means how many CEPs will be there. So even there also will perform do the efficiency test of condensate extension pumps. Then there is a circulating water pumps, that is called CW. So CW, as I told, so each CW again rating will be somewhere around 1300 kW. So 1300 to 1500 kW. So 1500 kW one pump. So again each boiler, each unit will have a two minimum running. One may be standby, or they have a one or two standby for the, if it is a stage. If it is stage, you have a common heater, one or two pumps will be as a standby. Then there is a cooling towers. So cooling towers are huge. Maybe some cooling towers may be natural trapped, some may be forced trapped. So we will able to do the performance test of both, either cooling towers, like this. Cooling towers will be having a fan. So fan means automatically auxiliary power consumption higher, but both have advantages and disadvantages. Sometimes we can see some of the auxiliary wise, wherever cooling tower is there with the forced draft, their auxiliary will be little higher. Where natural, but overall efficiency, sometimes we can find overall efficiency of the system in natural gas based power plants is good. There is, even though we have to find so many coastal based also, particularly north, they will work very well. North in the sense because they have a huge delta T available, particularly in summer very hot, winter very cold, so they can able to have a huge delta T. We can able to, the cooling towers will perform better. Whereas CT fans, of course, CT fans were the forced draft fans, then PA fans, that is a primary air fans again to supply air to burners through mill, the coal mill. So again, coal mills, each boiler will have a minimum 6 to 7 mills, and after them 5 will be working, 5 or 6 will be working. So those are the equipment we further divide when we are doing the analysis of energy audit in our scope. All this will cover, and try to give a efficiency test and also the performance test, and come out with a benefit analysis, that is saving areas in each and every area. In addition to that, some more further is like insulation, because they have a lot of in a boiler they have insulation, there is a steam lines, there is insulation. So all this again we do the thermography test. We have a thermal imager, we do the thermal imaging and of all the surfaces, and we'll find out where is the heat loss, how much heat loss is taking place, and we'll come out with how much existing, what is the thickness insulation, how much extra I think insulation has to be improved. Those also we do. Then also there is a transformer thermography we do even for transformers of the switchyard, because for transmission again there will be what are the hot spots in the distribution. There may be 220 kV switchyard etc. is there inside the plant. So there again, so there is a hotspot because in naked eye you can't see. So those things also we carried out in the part of the, in case it is a scope of work it is there, we'll do that also. Then fuel oil system, because though we talk about coal handling, there is a fuel oil. Why fuel oil is required is whenever you want to start the boiler, because we can't start with coal. So initially we have to start with furnace oil or LDO will start, and once it is stabilized, that burners will cut off. So that's why, so there is a huge consumption, in the even fuel oil. So that also part of the energy input. So for the energy input, what does it mean? Two inputs, one is a furnace oil or a fuel oil, another is a coal. So there are two inputs. Then what are the outputs? Outputs is only power. So those things, because if detailing is easy, so to calculate overall performance, overall efficiency performance, output by input, but you have to evaluate each and every system. For that, there is a set of standards are available, set of procedures available as per the. There is so just I'm giving one overall performance of a power plant. So this is 500 megawatt power plant, sorry, 1000 megawatt power plant of say into 2 into 500. So 2 into 500. So whatever are the inputs. Of course, I didn't tell about water. Water also major input because that is not contributing for energy, but water also major input. So nowadays we are performing water audits, and also we are calculating specific water consumption to produce 1 megawatt of power. So then what I already told. So whatever you are generating, say 1000 megawatt. Then there is 80 megawatt internally consumed inside the plant for auxiliary power. So only 920 is exported through this. GT is not gas turbine, it is a generator transformer. This through generator transformer will step up to 220 kV and finally distributed. So this is the typical. So furnace oil will be consuming, then as a coal, you can see coal how much you are consuming. So typical power plant, we'll see the what is the efficiencies where we are losing. I'll give one again Excel graph or the table, so we can know how much actually energy input and how much we are losing in each and every area, so that we can able to concentrate. So this is the HBD diagram we call, that is heat and mass balance diagram we call. So in this, most of the design data available, because that's why in most of the energy audit, so we will able to collect this data. This diagram will collect it for each stage, because many of the plants, there are the different stages of different era. Some are plants are some 1960s, some are constructed in 75, then later 90s. So each there is stage wise. So they have a different HBD diagrams. We collect it and see where is the further margin. So this is the called HBD diagram. So this already showed that because now Government of India, that is through Bureau of Energy Efficiency, they have identified designated consumers and found there is a power stations. These are power stations are the major contributor for the consumption, and also there is a saving potential is huge. So I am giving just one example, because very difficult to give again, though it is a design stage, okay, something is there, but what is the actual? So what is the actual? We now Bureau of Energy Efficiency collecting data for 3 years. So 3 years, suppose you want to keep a target. So I cannot give a target to overall, because we know that nowadays the typical supercritical boiler, their efficiency, their heat rate will be 2200. But I cannot give you that is the norm for all the power plant to do, because even if you give that norm, nobody can able to achieve it. So we should able to give a target, or a specific target is achievable target. So achievable target, how can able to fix it? So can't fix for only suppose all power plants also different generic or different say 300, 200, 210 or 500 or 800. So that's why Government of India, what they have decided is, will give a target for individual plant based on their past year performance, 3 years performance. So for that we can see, though I have said around 2200 is the design. Now we can see this is a baseline. Their heat rate is almost up to 3000. Though imagine there is 2200 is the design even at the 1970s, but people are still operating at 3000. So for that, this is their annual generation, that is in million units, and this is target 3087. That means this unit, so Bhusawal thermal power plant, they had to reduce their heat rate almost all 87, 72 to 87. See how much, what is the difference? So we can able to reduce it to almost 90 kilocalories. They have to reduce. Similarly, there is Chandrapur near Nagpur. So their design heat rate is 2920, 2733. So that means these people has to reduce more than 200 kilocalories. So like Dahanu is one of the best power plant. You can see out of this entire, it is earlier managed by Reliance Energy. So Reliance Energy, Anil Ambani, now it is under the flagship of Adani Group. So 2530, and for them their target is only 2519. That means only hardly they have to reduce only 11 kilocalories. So just 11 kilocalories they have to reduce as a target to reduce to meet so that they cannot be able to go to negative. Then Kakrapad again, it is a Nagpur. So these people have maybe another 80 kilocalories. The Koradi again, they were 3496 and 33199. So like that, there is each power plant. There is a PAT means perform, achieve and trade. Once you have given a target, this is baseline. 3 years back. Now this is the actual generation. That is when the baseline is fixed, this is actual generation, and this is the target. So if you are able to meet the target, or if we able to reduce, that is difference, that is a difference in heat rate and also into generation, we can able to convert into kilocalories. So that is the your achieve divided by the 10 to the 7, because divided by the your we are convert into oil equivalent, oil, because 1 ton of oil equivalent or 1 kg equivalent oil equivalent is 10,000 kilocalories. So we divided by 10,000, because we are talking about tons, so we will divide by another 1,000, so we convert into metric tons of oil equivalent. 1 metric ton of oil equivalent is called 1 energy saving certificate. So 1 energy saving certificate, so that will be given as an incentive, suppose if they are able to achieve the target. So now we'll see some of the, though we are talking about huge heat rate difference, this plant has having almost 200, 120. What is the effect of 1 kilocalories? Because now all the Exergy we are talking about kilojoules per kg. So kilojoules per kg, here I am talking about kilocalories per kg or kilocalories per kWh, kilocalories per kWh. So I'm talking just see one of the power plant, what is the effect? So one of the power plant that their target is a baseline 2464, whereas their the target is 2513. That means if you are able to achieve this one, but I just for to calculate what is the effect of 1 kilocalorie. One effect of 1 kilocalorie in this case. So just see, assume there is a 2564, you able to reduce just 1 kilocalorie. So 1 kilocalorie if you able to reduce for this power plant, so he can able to get energy saving certificate, 1,000 energy saving certificate he can able to get, and one energy saving certificate cost in the market, what is the notional value given by the government is 10,968 rupees. So 10,968 into 1,000. So that means 1 crore. So this one crore they can able to get extra benefit. The government wants to give a incentive for this energy savings. So now imagine now if they able to have a target of say able to achieve 100 kilocalories or even 50 kilocalories, imagine they can have able to get a benefit of almost 50 crores, 50 to 50, 60 crores they can able to get benefit. In fact, people have achieved in some of the cycles, that is PAT 1, PAT 2. Now we are talking about PAT 3. Now PAT 4 is there running. Some of the plants able to achieve more than even 100 kilocalories, and they got the benefit that they got in terms of energy saving certificates. Though energy saving certificates are tradable, like our market, we have a India Energy Exchange, IEX. In Indian Energy Exchange, we can able to trade those energy saving certificate, and they can able to get benefit. Nowadays, people are talking about distributing the energy saving certificates benefit to all the employees in terms of their incentive, because it is a combined effort of all the employees. Because one single general manager or a single power plant head cannot do or reduce their energy efficiency or reduce their heat rate. So it is a combined effort of all the people, either it is mechanical or electrical, or if it is all the group effort. So now they are thinking of how to distribute this energy saving certificate, because if they are not able to utilize, they can able to take it to the next level, that is for the carry forward. The energy saving certificate can carry forward, and they can able to sell in the market in the next cycle. Just I am giving one more example how we do for typical energy analysis. I will later on I will come to because this session is more of a Exergy. So we'll do the Exergy analysis of the major plant equipment. I will talk about. So I already told, because this is the auxiliaries where one we have boiler. So boiler is the energy input. Then there is a after, because boiler again to run the boiler we can FD fan, then PF fan. So this is the major for air supply. So there is a one typical power plant of 210 megawatt. You can see the load. There is a 1.4 for megawatt. Actually, I am not talking about the motor rating. This is the actual power consumption for hourly basis. So 1.45 megawatt is the FD fan. Then PF fan 2.7 megawatt. Then coal mills almost 5 megawatt they consume. BFP, because this plant has 3 BFPs, so it is a 333, so almost 9 megawatt is the power consumption. Then there is a after condenser, whatever the power generation, it is a HP turbine or a AP turbine, there is a LP turbine, there is a condenser. So after condenser, so there is a CEP, condenser extraction pump. So there is, of course, this is a almost 300 kW, two pumps are running, so it is around 300, 600 kW. Then there is a, to cool in the condenser, we have to supply cooling water. So cooling water, either from the sea, nowadays some people are having a sea water. So wherever there are coastal areas in suppose in Vizag, that is Simhadri. So they use the sea water for the cooling the condenser. But other places where there is sea water is not available, so you will be using a source from the river or the canal. So that water we through cooling tower, so we will supply to condenser and afterwards again get cooled in the cooling tower. So then there is ID fans. So once your flue gas is after heat recovery in APS, that is air preheater, so it is goes to ESP, that is electrostatic precipitator. Again, electrostatic precipitator also consume almost all 800 kW. And finally, the FD fans. So FD fans also, see the typical power plant has a 2 FD fans. 2 FD fans almost 2 megawatt each. So 2 megawatt or 3.5 megs is a actual consumption. Actual consumption. Finally, it is sent to the chimney. So this is, we will be measuring. We'll be measuring performance of each and every equipment, each and every area will equipment, and we calculate the efficiency. Of course, we normally we do the first law of efficiency use using the input-output analysis, because we know what is the power input and is output in terms of either is a air or in terms of water. So those efficiency we calculate and will come out with the areas where we can able to improve further. So far we have carried out almost, like I said, around 40 power plant. So some Neyveli lignite having a 7 into 210 megawatt we carried out. Then NLC again there is one more NTPL, that is a TNEB and NLC joint venture. This is a TNEB and NLC joint venture is called NTPL. There is a NLC Neyveli NTPCL. Tuticorin, that is 3 into 500. Recently we have done it. In RTPP, Rayalaseema Thermal Power Plant, in VTPS, Vijayawada Thermal Power Plant, Raichur Thermal Power in Karnataka. Then there is a GN Guru Nanak Dev Thermal Power Plant, Sikka in Gujarat, PTP Paricha in Jhansi in UP. There is Sanjay Gandhi Thermal Power Station, Bir Singhpur in MP. Then Rajiv Gandhi Thermal Power Station, that is a 2 into 600. This is all again not super critical. It is a Chinese makeup boilers. Then HTPS Korba, then MBPs in Chechai, Kota in Rajasthan, Sarni in MP, then Blue Water Power Plant. So Blue Water Power Plant in actually in Australia. So there also they have some. They are called us to do the energy audit of their power plant. Is a 2 into 313 mega power plant in Perth near in Australia. Then Lanco gas power plant in Kondapalli in Vijayawada, Doran gas based power plant in Anand near Gujarat. Then Navabharat, of course, though this popular steel, so still majority of the steel plants are the cement plant nowadays having a captive power plants. Then Indian Metals and Ferroalloys, Cuttack, they have so many power plants. Then Sri Rangaraj Ispat, again they have a power plant. So many power plants we did, and based on that we have to come out with the. And also water audits. As I said, water audits nowadays people are asking us to do. Here also you can do Exergy analysis. So why I am giving the water audit also, there is a recently one of the student has taken up as a Exergy analysis in pumps, CW pumps in Rehan, NTPC Rehan. I will be telling about the case study. Then Vallur, there is a Dadri, Ramagundam, Korba, Simha, there is so many power plants. So in fact, we have big list goes to almost more than 50 power plants, and also water audits around 20 power plants we did. And based on that, we can be now. So of course, many people already talked about Exergy. Exergy, I don't want to again repeat what is Exergy. So again, we are talking more of a quality. So whatever energy we are doing only mostly in using first law of energy efficiency. Of course, Exergy, I'll give one example where we can able to apply Exergy analysis in a particularly condenser, and we'll do how we able to do it, and where we can able to apply. Again, though morning Sudipti Day, sir also talked about Exergy when it is coined somewhere in 1956. Though frankly speaking, though my company name is Exergy, we are not doing much about Exergy. Just for the academic purpose, we had just taken up one or two analysis. So this I told about condenser, because condenser, so we'll do analyze the condenser, where the power plant, where how much we are losing. So it is a typical LP steam, and also we are giving a cooling water. So cooling water to cool at least to recover, because not for temperature recovery, just for to recover DM water. Otherwise that also wasted, particularly. So if you want to recover, then is a CEP. There is of course pump. This is a CEP is condensation pump. Then to deaerator, in between there are LP heaters. Just we'll talk about the system, condenser system. So before that, so as I told, so anybody can able to in chart can able to write about what is the where we are losing major efficiency, because we told about energy is energy efficiency of the power plant is hardly 31%. So remaining 70%, 69 to 70% we are losing. Where is the equipment where we are losing? So just for the purpose of analysis, I will give one Excel sheet where we I am giving as the condenser performance. Though I said condenser performance is a 210 megawatt, but most of the power, because there is a recent data where we have done one of the power plant. So you can see the actual generation. Actual generation is varying 170, 185, 160, 163, are operating at low load. Why? Because problem is nowadays in India we have a surplus power. Because we have a surplus power, though earlier we talked about there is a power shortages, power failures, power shutdown, power cuts, so many. But practically now we have excess power. So people are, suppose they have 5 units, they operate only 3 units. Even have the 5 units, even 500 megawatt, they operate at 350 megawatt, because there is no takers. Because industry, though we have nowadays the thermal power plant, now addition to that there are now solar power plants, they are into the system. So that's why, so we have a surplus power. That's why now I cannot ask the unit to operate full load, because even if you wait for 2-3 days, they're not able to give a full load. So that's why we are taking audit. We are doing the audit as run basis. Whatever load they are running, so we take the data and we are analyzing and giving the data. So just at least for design purpose, design stage, I'll give an example. So we have a typical, what is it, heat duty? Heat duty of just condenser. This is almost condenser A and B. So here I just calculated, this is a 210 megawatt. So we are dumping heat duty equivalent to almost a 331.4 megawatt. So we are talking about 210. Suppose 210 means maybe efficiency, maybe we have to lose some 30-40 megawatt. But we are in fact, practically we are dumping even at low load almost 300 more than 300 megawatt. So 300 megawatt of equivalent energy we are dumping into the cooling tower in the condenser. So that is the inefficient equipment. So even if you are able to improve some even 1 or 2%, so that will give a major improvement for the overall cycle improvement. So that means what is how much we are losing? We are almost 150%, 150 to 160% of energy we are dumping in the cooling tower. So now we'll do the Exergy analysis. So this is the overall plant 210. So what is the input? So input again I am giving one pit is around 147 tons of coal will be your consumption hourly, 161 tons per hour. So heat rate about it is the gross calorific value and heat input. So heat input in terms of the total heat input. So what is the heat input in convert into megawatt hours? Megawatt, it will be 600. So though you want to produce only 210 megawatt, where actual heat input is in terms of megawatt is around almost 600. So 600 we are giving input. Finally we are getting only 210 megawatt. So that means overall efficiency at the design stage 34. But whereas actually we are getting only 30-31% efficiency we are getting in actual practical. So then what are the losses? Almost we are losing 65, almost 70%. 70% we are losing. So again further we analyze where are we are losing. One is in condenser. So condenser itself we are losing almost 55 to 60%. Then boiler efficiency somewhere around 85%, 88%. That means boiler we are losing 12%. So that means we are losing here 53 and 60. So out of 65, these two major equipment. So these two major equipment, we can able to improve performance whatever possible. So that means our work is done. Our work is done since our whatever for the energy audit improvement. So we can able to reach the target whatever given. So here, so what we are to further analysis, because our purpose is to do the not only energy analysis to Exergy. So we have put some values based on the inlet outlet conditions. Inlet outlet conditions. So inlet is somewhere. This is the your hot well temperature. Hot well temperature when you are cooling through cooling water, so it will come to the saturation temperature for that steam. So you will get a 46 or the 43 the saturation temperature, and once it is out, so we can able to get a cooling water out temperature. So suppose a cooling water temperature earlier slide I showed, because this is the north, so temperature is going even lower. So we are getting a temperature as low as even outlet temperature 26 also 20 degrees, because of winter, so temperature very lower. So we got so we analyzed what is the entropy in, entropy out, and also what is the exergy in, exergy out. So that is the total exergy. Total exergy available is already the enthalpy difference into your temperature into your entropy difference. So based on that, we calculated into mass. Into mass, we calculated is so 2215 is. So this is the we can be able to do Exergy analysis, but how to improve? How to improve again? Because I am not we can particularly pinpoint, because Exergy analysis where we can able to improve, because finally we have again in this case also we gone back to our traditional method of energy analysis, and we told them, so where are the further improvements? So we have calculated the efficiency of this condenser, that is performance of condenser. Then we are, because this condenser is linked with the cooling tower. So cooling tower, again we have checked the what is the temperature in and temperature out, where we can how it is the cooling tower performing, is there possible to improvement. Even 1 degree performance we can able to improve the 5 kilocalories heat rate. So 5 kilocalorie heat means we are already told 1 kilocalorie equivalent to 1 crore. So even if you able to 5 kilocalories improve in the performance improvement in the cooling tower and condenser, there is huge benefit. So then again, based on the cooling water temperature, based on the your inlet outlet temperatures, and also the vacuum maintained. So they all depends on the again the cooling water temperature. So this we have again evaluated where there is a possibility of because I can't improve the heat transfer. So heat transfer is fixed. So existing condition, is there any fouling on the heat transfer coefficient or reduction in the heat transfer coefficient because of fouling? Those things we checked. Then what is the cooling water flow? So cooling water flow particularly is not a problem, because many times the plant has to operate at 210 megawatt, but they are operating only 160 megawatt. But cooling water flow is same. Cooling water flow they are giving almost 28,000 meter cube per hour they are giving. So here there is optimization potential is there, optimization. But problem is they said they cannot able to run with a single pump. So they operate after 2 pumps. I said we told them maybe you can go for a throttling, but because these are very big pumps, no, they don't want to take any risk of throttling the pump. So whenever they want, otherwise they can able to go for a variable speed drives. But variable speed drives, particularly HD drives, nobody wants to go for it. Another thing is because it's a generating station, their cost of power, they take only 2 rupees 50 paise for cost of power, whereas we are getting power at maybe 8 rupees 9 rupees. But 8 rupees 9 rupees we can able to quantify and tell them there is a you can get a huge benefit, and there is a payback period. But problem is for them is their cost of generation only 2 rupees 3 rupees in between. So that's why, so there is a payback period is very high, they cannot go over it. So that way we have to see where all the optimization potential is there. We told them there is you can improve the impeller efficiency, and also the casing efficiency by some coating. So you have a coating nowadays available, maybe you can able to 3 to 4%. We ask them to do for one pump. When they pump practically we have showed there is a 5% saving. So 5% saving was there in one of the pump. So based on that, they took up another pumps for improvement. So that is given improvement. Similarly, we asked them to some of the pumps, because of energy efficiency, people have told them because winter they have they stopped it because they're favorable condition. we told them, so but the fan capacity is only 110 kW. So 110 kW they stop. So but it is giving effect on the your basin temperature. So we are told them, don't stop the fan. You may operate one more fan and able to see, we can able to improve the overall heat rate the turbine by running one fan, though maybe extra consumption of 1 kW, but it will giving a heat rate improvement. So those things we showed. So these are the things we normally practically apply in a power plant to improve the overall performance of the any equipment, because I am talking only condenser, but any equipment we can do some the first law of efficiency, first law of thermodynamic efficiency, we do it, that is energy analysis. But of course exergy analysis later if we require, but so far no client has asked us to do exergy analysis. So exergy analysis already showed, this is exergy analysis. Then this is one of the power plant in Vijayawada thermal plant, though we did the energy audit, but exergy analysis we not done it. This is done by one of the student as per his thesis work. He has done it and published. This paper is available in the Google. So he searched it. So he has given a exergy analysis each and every equipment. So we have either economizer analysis, in and out, superheater, then there is a HP heater, LP heater, IP, then there is a condenser has done, inlet outlet, deaerator, BFP inlet outlet, LP heaters. So like that, every location he has done it and has come out with the analysis. But problem is, after doing so much of analysis, see what is the pinpoint. So where we can able to exactly save energy or improve the performance. So that is lacking even in this article. So they could not able to tell clearly where are the areas where they could able to improve efficiency, total they can able to overall performance and to reduce. In fact, this plant, though Vijayawada thermal power stations, we say they have so many awards they got it, but we have done recently their audit and monitoring and verification audit. So they were forced to pay. They were forced to pay penalty because they could not able to improve during the assessment year. Their performance very poor. So they were end up with paying almost 40,000 EC, that is energy saving certificate loss. That is 40,000. Imagine 40,000 into 10,000, almost 40 crores penalty if they are not paid. But when the market rate was when there are 1,000 rupees, so they bought at the market rate and they paid the penalty. So this is the first law of efficiency, because comparison between first law efficiency, second law efficiency. This is a boiler 88%, condenser efficiency. This is a first law efficiency comparison. Then similarly, we will do the second law efficiency. This is again second law of efficiency, and also there is a percentage energy destruction. So how much energy is destructed in his. So overall power cycle where there is a in this plant, particularly in the Vijayawada thermal power station, the loss is 62%. And different equipment, each equipment they have done it and they showed. So what are the how much which equipment has to be concentrated on to improve the performance. Similarly, of course, same thing. Yes, they have the student has projected in terms of graph. So where are the exergy efficiency? Exergy efficiency of condenser is only 20%. How much you can able to further improve? Because so that is one of the area we can able to future further we can able to do recommend. And the only thing is we have to do the cost benefit analysis to improve. Whereas for the energy analysis we are familiar. I can able to tell them. So you do like this, you do like this. So there is investment of this much. We can able to improve and we can able to reduce the overall efficiency of to meet the targets. Similarly, what is the energy destruction? There is a condenser. There is energy destruction almost 16.1 megawatt. Similarly, there is a energy destruction of different components. Then there is a energy analysis versus exergy analysis. So condenser. So as per the energy efficiency showing, there is a almost 36%, whereas exergy analysis shows it is only 20%. So yeah, because condenser, why you have taken already, people are talking about grading, that is high grade, low grade. Problem is we are cooling or we are getting a cooling water exit temperature at somewhere around say we are cooling from 30 to say we are giving a cooling water at 30 and cooling water coming out 40, but 40 degrees centigrade, though we are dumping almost 330 megawatt power, so we cannot able to recover much because it is low grade. So that is a quality of is very low and Exergy is very low. So that is the so for the further improvement, as people are talking about morning also, we can able to have a flue gas analysis further. Suppose now people are talking about only 140. If you able to reduce further, maybe you can able to reduce the overall efficiency, and also you can go for a, instead of steam, you can go for a organic rankine cycle (ORC). But problem is we can't be able to produce a organic rankine cycle system for a typical maybe 500 megawatt or 800 megawatt. People are now talking about only 4 megawatt, 5 megawatt system. People are talking. So those things are already available. Already available. Many of the cement plants already implementing and ORC, that is organic rankine cycle, and able to recover low grade heat. And some extent, people are now talking about small chemical plants, about heat pump efficiency. So we can able to boost up. So somewhere we have a temperature of low grade heat somewhere around 60 degree water. So 60 degrees we can able to heat it up to say 80 degrees. So 80 degrees we can able to use it for some of the process requirements. So this is the one of the, and again I'm talking about recently one of the student came to our office for her internship as part of her MTech. And she she was participated in one of our energy audit in the thermal NTPC power plant. So though we did a performance of so many equipment, she particularly concentrated one of the cooling water system. So cooling water system, she did a performance analysis. One is both the energy analysis, what is the efficiency, and also Exergy analysis. This is the data she collected and analyzed, and she even published a paper. Recently, she published a paper last year. Again, it is online seminar she published, and can see here. So this is the outcome. Outcome is there is a potential to, by Exergy analysis, there is a potential to improve efficiency of these pumps about particular, because all pumps having not having same efficiency, because they are each having different efficiency gap. So CW1 we can able to efficiency improvement of 7%, because we have seen each pump is a it is almost 1500 kW. So 1500 kW pump we can able to improve efficiency of 7%. Imagine how much you can able to improve overall in the plant itself. You can able to save megawatt. So many megawatt you can able to save in this plant. Then 1C is a 4 point. So 1M is, that is unit 1. The pump A, pump C. That means there is a B is standby. Similarly, unit 2. So it is a CO2AB. I think here it is a 3 pumps are running, stage 1. That means they have a common header, so they can able to operate only with 5 pumps. They can able to operate with the 5 pumps, and two pumps will be, or 2-3 pumps will be standby. Similarly, stage 2. So stage 2, of course, Rehand all are having a 500 megawatt. Here again, they able to operate only with 4 pumps. They operate with 4 pumps. So here is saving potential is 8%, 7%, 8%. So this pump only having 4% improvement. So this is the Exergy analysis shows saving potential. Suppose if you based on the with energy analysis also almost similar trend, only that variation is around 1 or 2%. 1 or 2% is the variation. And recently that paper was accepted and was presented in this recent, I don't know, many of you may be knowing, the innovations in sustainable energy and technology. This virtual mode recently happened in Bangalore. So there this paper was submitted and it was published. So my name was also given as a co-author, and also VIT professor and a student. So 3 people name was there in this. So now I'll invite question and answer session from you. So how we can do? We have done Exergy analysis of some of the equipment, and in practical situation we are not utilizing it. So this is very old. We are talking about Exergy 1956. Though my company name is also Exergy, but still we are talking about more of a academic purpose, analysis purpose, but practically utilizing and improving the performance at the design stage, because particularly still we are many of the equipment and the particular energy audit point of view. So people will call us only when the plant is running. When the plant is running means everything is all designed, everything is done. So they call us only to improve, at least to meet the design stage, because there is a lot of gap is there. So we have seen some plant is designed for 2500, whereas they are operating at 3200. There is 700 kilocalories gap is there. So those plants still working in India, still working. So those there is huge potential is there. In case they are given targets, in case they don't achieve the targets, there is a penalty. There is a huge penalty, also huge. That's why people are very worried about their penalties, and that's why they are able to do energy audit and improve, and every year by year, they have already, now we have come to PAT 3 cycle. In PAT 1 cycle, we have saved almost all 38,000 crores of rupees. 38,000 crores of rupees in equivalent energy we have saved in PAT 1 cycle. In PAT 2 cycle, still they have to quantify. So how much energy is saved, quantified by all the DCC. DCs means designated energy consumers, designated consumer, energy intensive consumers. So we'll see future what are the we can able to. So I will stop my sharing. So any doubts, any questions? Hello, I'm
Hello,
audible,
sir.
please.
Thank you, sir. Thank you for your nice presentation.
Hello.
Good presentation. Yes, sir. Can you hear me?
Hello.
Hello, sir. Can you hear me? Okay.
Hello.
Hello. Yes, participants, dear participants, if you have any queries, you.
Yeah, I'm done with my presentation. Any doubts?
Yeah, yes, sir. Thank you.
You're
Thank you for
welcome.
the nice presentation.